from
solenoid.
It's moved from near, I think,
Which is
a
moving?
magnet.
Magnet
The
moving, or
magnetic field
both are
will-
moving, or one of them is moving?
One of them.
One of them, that's right. Yeah.
Then
So if you both of them moving, do you think we can handle that problem? If both solenoid and then magnet is moving, do you think we can handle that situation or describe that phenomena? Lenz law. So Lenz law is Lenz law is supplementary of the Faraday law. It gives additional information because Faraday law, I put them side by side. That is a Faraday law. Faraday law. Faraday induction law. Induction law. So they are very relevant, right? Lenz law is just the wording. So Lenz law say if they are, do you know the Lenz law? What does Lenz law say? Do you remember?
When a charge is moved near a magnet, I think the magnet will oppose it.
Magnet will oppose. Which will oppose that?
Oppose the movement.
So which will approach stop which? So basically, can we just consider single coil without considering the solenoid? If you can understand what's happening in a single coil, you should be able to understand Lenz law. So basically, you are talking about a magnet is moving, right? Oops, dark color. So you have magnet here, right? So this is a magnet. And can we say the north is downward, is at top, at bottom? So that is a permanent magnet, right? That's the north, this is south. Now, if this is a metal, so this coil is made by a conductor. So if you just make how to say ammeters. So if you put ammeter here, so there's no battery. Remember, there's no battery here. It's just the ammeters. This is ammeter, which is connected with this loop. Okay, this is a 3D diagram. See, so this is a 3D diagram. So basically, this is the center. So what would happen? So basically, Lenz law say what would happen if, for example, if the magnet is downward, is moving. Do we have any current here? If there's any, which direction? Maybe I will draw much more detail. So this make sure you can see this part of a 3D diagram. So obviously this is a front. This is a back, right? So you can so this is just standard, but this is a wire. This is a single. It's called a single turn coil, right? So what would happen? That is exactly Lenz law will tell you. What would happen?
Then
according to the Faraday law, what would happen? According to what Faraday law, what would happen?
It would generate electricity, I think.
That's right. So basically, if you even we can put a resistor here, because resistor. So if I put a resistor here, let's just redraw this part. You put a resistor. You put a resistor here. R, can you see we use R? The tiny Q, this represents a resistor R. According to Faraday law, when this happens, and this experiment is equivalent to this experiment. You see, put ammeter, and you put the resistor here, and this will become, so this become the battery, can you see? Depending on the direction of move, right? So it could be equivalent to the battery. So this is called the EMF epsilon. So according to Faraday law, do you remember what is epsilon? It's called induced voltage. Induced, do you know the formula?
I think there's an N naught in there.
Sorry?
There's an N in there. I think it's N.
Which is N?
I don't know. I don't remember.
Induced EMF. It's called the EMF. Or you can simply call it induced voltage. It's the same thing. So they become a battery. All of a sudden, this coil became battery. So according to Faraday's law, yes, you have multiplied N here, but in this case, our N is equal to 1, right? In our case, this what is N? So can you write a formula here for you? Do you remember this formula? So this is this N is a number. This is the number of turn. How many turn, right? And in our case, in this case, the number of turn N is equal to 1, right? Just single turn. So that is I put it down here. When we use a single turn solenoid, so this is just N equal to 1 turn. How about this phi? Do you know the phi? So the induction is to the complete name is called
AB cos
AB. Yes,
theta?
AB. Yes, that's right. That equal to A, the area multiply the B for magnetic field, right? Now, if that is for the uniform, okay? If this is uniform, if you know, you have to use this formula. Otherwise, you have to use this one. You have to use integral. So otherwise, you have to use integral. So you have to use a B multiply dBA, right? So if B is not uniform, you know the uniform. So for example, if this area here, the magnetic field is just a constant, right? Okay, we say can use this color to represent magnetic field. See, if the magnetic field is a constant, right, uniform, and then in this case, you can simply, so this is A, right? Is this in this case, the phi will simply equal to B multiply this area, so that is this area. So that's Faraday law, right? Or if there's an angle, so can we just go to another scenario? If there's an angle, between the magnetic field and the area, if this is a magnetic field direction, right? Or perhaps we just go to upward, because you can easily draw that angle. This time it's going upward, the magnetic field. So if the magnetic field is toward one direction, but they are not, they have angle between the normal direction. When we study vector in mathematics, we know we use this n. Do you know what's n? The direction vector, right? To represent this area. So we are still talking, the value is this area, but the direction is this small arrow here. So therefore, if this angle is theta, then in this case, phi, in this case, A times B is a different scenario. But in this case, even the B is uniform, we have to multiply the cosine theta. That is, can we use B here? BA cosine theta. Have you studied this formula?
Yeah.
Yeah, so this is called magnetic flux. flux, as if it's just like a fluid, but it's not. It just describes the direction and the strength of the magnetic field. Okay. So this is flux according to Faraday's. Now, do you remember the magnetic field distribution in this case? How to describe the magnetic field in this case of permanent magnet? In the middle, from north to south, right? And then back to south. So that is the central one. But the one besides that, this will go that way, can you see?
Yeah.
Go other way. So that is how to draw the magnetic distribution if you go all the way back. So that is magnetic field, can you see? So from this diagram, you can see that the closer to the North Pole, the stronger the magnetic field. Do you agree? So what would happen? Question is, when this magnet is moving, what's happened to the flux? Does the flux increase or decrease?
It'll increase.
Why is it increase in this case?
If it gets closer, then more of
so we just consider one. So the N, we just saw, so this is first scenario. The N pole, North Pole, is downward. Okay, is moving downward. Is moving downward. So you think the flux will increase? Why? Because in this case, flux can be equal to A multiply the B, but the B is increase, right?
Yeah.
So since big increase because B is getting increase, right? So according to Faraday, then you can measure, you can work out this voltage induced. Now, if there's voltage according to Ohm's law, if you can see the voltage here, do you think there's current moving in this circuit according to Ohm's law?
Yes.
Yes. So the current will move, right? Now we don't. Faraday law doesn't tell you the direction of current. They only tell you that there's voltage induced, right? So Lenz law is invented to describe the direction of current in this circuit, or the current you read from your ammeter. Do you understand? So what would happen? Can we just go to another scenario? What would happen? Consider if the same setup, the North Pole down, North Pole is leaving, is moving upward. What would happen upward? What is phi? Phi will change?
It'll decrease.
It will decrease, okay. Because B is changing, right? So according to Faraday's law, in both cases, now the d phi dt is not equal to zero. It's changing. Do you agree? Because phi is changing, right? Is changing. But Faraday didn't tell you the direction of current. So Lenz said, well, I can tell you. And if this happens, can you say consider the first scenario, right? The North Pole is downward. And in this case, Lenz law says there is induced current. There is an induced magnetic field to stop or to reduce the change. Can you see? So can we use the red color? Can you see? There's additional magnetic field. In this case, they were built up against the change because the local field is increasing and the coil will generate the magnetic field to reduce the change, slow down the change, or resist the change. This field is called induced field. Okay, there are two fields now. This is magnetic field. This is called induced field. The red color one is called induced field. Can I write down here? So this B, induced field. We put in here. So according to Lenz law, that is Lenz law, if the flux increase, if the B is increased, all right, and the B induced field, this is called induced field, this is called induced field, magnetic field. Magnetic field. Will be opposite, okay? Will be opposite to B. There are two vectors, can you see? There are two vectors. Okay, how can this induced field exist? We have to go to this simple example again. If you have a coil, this 3D coil, right? If you put, so this, again, this is just part of, this is a part of a cylinder. We just draw one of them. So this is just part of cylinder. So you know this is a 3D diagram, all right? This back is the front. So how could it be possible to generate the magnetic field at the center upward? We only have electron in the conductor. So you can imagine that there are not of electron in the conductor. You see? EI. There are many negative charge in the conductor. Do you agree?
Yeah.
So how can we so this induced magnetic field, right? Induced magnetic field. So can you work out to what direction the electron move so that they can generate such the induced field upward? Have you studied the magnetic field near the coil?
Yes, I
Yes,
think.
good, that's good. Okay, think about it. Sometimes you need to actually, if you can do experiments.
Would they move down?
No. The electron can only move in two directions. They can only move this way, or they can move this way. By which way? To which way that they can generate the right direction of this induced field? Do you know my question?
Yeah.
Maybe I probably will draw another one. Maybe in your textbook, you know this one. So if there's a coil, okay, I use this color to indicate its conductor. And if you have the, just say, again, this is part of 3D diagram. So you know there is a back, there's a front, right? Now, if I just connect this with a battery, so if you just connect with a battery, so this is a coil, okay, and I put a battery here. If I put a battery here and put ammeter here, so which direction the current will move? Electrical current is positive. The current, which direction the current will move? Current will move from positive, right?
Oh.
No, other way around. Can you see? This is the front, can you see? This is how current will move, right?
Yeah.
So they will return to the negative, right? So this is by the way, this is called as current, right? But in this case, there's no battery, remember? It's just single coil. You probably got an ammeter here. So just set up that you got a resistor. So there's no battery. But according to Faraday, there's this coil will become the power source, a battery. Okay. Now, according to this diagram, if the current goes this direction, what is the direction of the magnetic field at the center? Upward or downward? Do you use the right hand? Do you know the right hand rule?
Yeah.
Because
Would it be
right,
downwards?
yes, downward, yeah.
Mm-hmm.
So if you use the forefinger to go through the direction, so the thumb will give you direction of the of magnetic field at center. It's called right hand rule. So you just put the whole fingers up this way, all finger around it, and the thumb will give you direction of magnetic field. So in this case, magnetic field generated in this setup is downward. Can you see? It's downward. Maybe I make sure this you can read this one. This is downward. Can you see? So it's opposite. So in our case, we, according to Lenz law, when the magnet is moving downward, and the induced magnetic field should be opposite, therefore should be upward. Do you agree? Now, can you tell me in this single coil, what is the direction of current generated?
This way.
Right, right. So that is the right way of current, right? Induced current. So in this case, I will call this is induced current. I put it in here, can you see? I in. So this is called induced current. Induced current will generate induced magnetic field. Does that make sense? Induced electrical current. Electrical current. Okay, you are right. So induced current in this case will go that direction. Okay. And the direction of current, or we can continue all the way, go here, can you see? And return. In other words, in this case, this whole setup is equivalent to this one. This is resistor R, and this battery here. So that is equivalent to this one. Can you see? The battery is upward. Can you see? This is battery, but this is just an electricity generator. Do you remember? Do you understand now?
Yeah.
That is exactly how the electric generator works. They just move in this magnet, or change the magnet. Can you see? Let's go to the first page. Can you see? So when you move this up and down, and they generate electricity, it's called AC. We know now when you're moving downward, the electric current goes that way, so which is correct, right? This induced one. When you move upward, according to Lenz, so can we just continue Lenz law? According to Lenz, is when can we just we can write the Lenz law here. You can compare these two scenarios. So in the opposite, if they're moving if you're moving upward, you see, if you move the magnet upward, so therefore magnetic field will decrease. Do you agree? According to Lenz law, and B induced field will be parallel, same direction.
Yeah.
Do you know? Does that make sense now? The induced current will generate the induced field to resist the change of the magnetic field. That is an important idea of induction. But Lenz law tell you exactly the direction of the current.
Yeah.
So this is Lenz law. So this is Lenz law. Yeah, that's Lenz law. Do you have any questions? That is
So
Lenz
we just
law.
have to remember this, if B increases.
No, you don't have to remember this detail, because in this case we have specified many things. Let's use the table. Okay, we use the table. There are many scenarios. You don't have to remember. So basically, can we just consider this? This time I draw a proper solenoid. So let's just draw a proper solenoid. So this is solenoid. Let's give me some straight line. So this is a solenoid, right?
Mm-hmm.
This time I draw a coil with more than one turn, so not a single. So what we do is I just draw the coil. So the coil go back and return. Can you see?
Mm-hmm.
And go back again and return. You see? There are more than one turn, right?
Mm-hmm.
So that's why when you use Faraday's law, that's enough. When you Faraday's law, you have multiplied this number of turns. How many turns do you have? 1, 2, 3, 4, right?
Yeah.
Then you can do many. So what happens is that if you just connect that one with ammeter, I use the white color. So this is ammeter, and then this is put a resistor here. So this is a simple electricity generator. Okay, I will make a table. So basically there is two scenarios. So that is one is I cannot copy this. So what can I do? All right. I don't draw this diagram. I just know that there are two poles here, right? We can work out the detail afterwards. Otherwise, I have to draw this again. I simply show you there are two poles, south and north, right?
Mm-hmm.
And they can either move downward, okay? This downward, or upward, see? So let's build the table to summarize all possibilities, all right?
Mm-hmm.
So the is equivalent. I use this one. Is equivalent. So this is a summary of what we have studied. So first, we know that when you're moving downward, the current is equivalent to this current will go that direction. Can we see? Is a battery is positive. Can you see?
Mm-hmm.
When you're moving upward, so the situation will be like this. So this is a negative and positive. You see that?
Mm-hmm.
So this is just making a table to include all these scenarios. We build a large table, right? It's just like we're doing experiment. We divide this into two scenarios, and so we do that two scenarios, and that's how you can summarize what you studied. You can build a table. Now, in the first scenario, the magnetic field is with the north pole down, all right?
Mm-hmm.
So that's how can we simplify. I don't have to draw this diagram twice. So it puts north node down. Another is north up, all right? There are four scenarios. So if I just finish this is north, this is south, right? Another possibility, this is north, this is south, all right?
Mm-hmm.
And the direction of magnetic field, there are two directions, move to the movement. So one is this is moving, is downward. Another is moving upward, all right?
Mm-hmm.
One is downward, is upward, okay? So this is the direction of movement. This is velocity, right?
Mm-hmm.
The velocity. So these four, they have two outcomes. Okay. So this is scenario A. Can you say this is in terms of the battery? This induced current. Can we call this situation is we have used A, B. Can we use this as one? Situation one. This situation two. Okay.
Mm-hmm.
Now let's move this first one. When the North Pole is down and is moving downward, we know the current now. Do you agree?
Mm-hmm.
I will just draw this one first. So this one, the current, maybe I will draw this. Yeah, for you understand. Maybe I will draw this cylinder here. I will draw a cylinder here. This is better than a textbook. See?
Mm-hmm.
You can summarize all scenario. You don't have to memorize anything at the end of the day. That's my point. All right. You just remember that. Just remember this: the reduced field is always trying to resist the change of the magnetic field. Does that make sense now? Mm-hmm. Always resist the change. In chemistry, there's a Chardonnay. You know the Chardonnay law? The Chardonnay. Have you heard of that?
In chemistry?
Yeah, in chemistry, there is a law. It's called the Chardonnay.
Mm-hmm.
I will finish this first, okay? So I just draw this scenario first. It's similar. So this is a natural phenomenon, which is the nature. So the electron now, basically the electron will decide which direction to go, given the direction of given the change of magnetic field. Okay.
Mm-hmm.
So in the first scenario, this time I just drew very quickly. So I just just three. Don't have to draw this full. 1, 2, 3. 1, 2, 3. Doesn't matter. We get this more than one number. 1, 2. Can you see this is a 3D diagram? Can you see?
Mm-hmm.
In the first case, we know the current we know the direction now. The current will go that direction. Do you agree?
Mm-hmm.
Or this one. That's right. Oh no, other way around. Other way around. Hang on. This one we go out. Can you see? So we know this scenario, right? If you can you work out the direction of current in another 3 scenario? So this scenario is equivalent to our scenario 1. Can you see?
Mm-hmm.
Scenario 1. Okay. Can you work out other 3 by yourself? Good. That is so this part became positive, right?
Mm-hmm.
So this is positive, right?
Yeah.
So this is positive. Sorry, this is positive. This is positive. So that's scenario 2, okay? Now, this time I change, this is S. What would happen if this is S? I just draw this diagram. The magnetic field goes that way. It's different now. Be careful. Yeah. Magnetic field is upward, can you see? Into the S, can you see?
Yeah.
So that is something you have to be careful now. So what is this scenario? Let's show this properly. So the central one is this, and then this. So originally the magnetic field is upward, which is increase.
Mm-hmm.
Mm-hmm. Okay, let's double check that one. So you think the current, induced current will go that way or downward, right?
Yeah.
Because that strength increase. Yes, you're right. You're right. So that's the scenario 2. Do you agree?
Yeah.
Scenario 1. Well, this is a summary of Lenz law. This page, single page, right? So this is Lenz law. Do you want to do some exercise to check?
Yeah.
Yes. So let's go to, do you have textbook? We can use a textbook as example. Do you have digital textbook? It's,
I'll
yeah,
see.
you can share your, yeah, let's just stop that. Because better use your example for exercise problem first. Then if you want to do more, we can invent something. Yeah, give you a green light. At the end of chapter, they all have exercise. Yeah, that's right. They have similar diagram. Yes, sometimes it's horizontal, sometimes it's vertical. Yeah, can we try this one? Try yourself. Can you try this one? Can you enlarge this part a little bit?
This one?
Downward, downward. Yeah, the top one at the top of the page. Can we go? Yeah, this one. Can you try? They have 3 options. Can you read the question? What is the question? Refer to the diagram.
Determine the direction of the current induced in the solenoid when the electromagnet is switched on.
Yes. This time, the source of magnetic field is electrical magnet. Yes.
When it's turned on, does it go from the long end to the short end?
Well, they from 0 to something. So if this switch off, this is the electrical magnet. If they switch off, there's no magnetic field. But when you switch on, they're from 0 to that constant distribution. And also from this one, you can know the diagram. You can know the direction of current. Can you see? Because this, I just show you. I ask you the question. Do you know the direction of current? Oh, that they tell you. Can you see? When it's on, the current is from positive. Follow this one. According to right-hand law, what is direction of the field of electrical magnetic field? This is called electromagnet. Generated by the solenoid on the right-hand side. So what is direction?
From positive to negative?
No, that is current. Can you see this? Can you see this color? They have drawn 3 magnetic field, magnetic force line. Can you see? That blue line represents the direction of magnetic field generated by this coil. Okay. Now, according to Faraday's law, do you think there's a current in the coil? In the first step, you have to answer this question. Any current induced according to Faraday's law? Faraday's induction law.
If the magnet is switched on, then yes.
Yeah, initially it's off, and finally it's on.
If it's off, then there's no current.
That's right. Which current? I'm talking about induced current on the right-hand side and on the left-hand side.
If the magnet is off, then there's no induced current, I don't think.
Well, you have to consider the process. if you switch on for a while, the current became the magnetic field become constant everywhere.
Mhm.
Therefore, you are right. There's no induced current. However, from the switch off to switch on, it takes a while to build up this magnetic field. Do you agree?
Mhm. Yeah.
From zero, from nothing to something. Does the field change or decrease or increase?
When the current is switched on, then it
Yes,
increases.
at the very beginning, yeah, at the first few moment, does the field change?
Yeah, it
Yes,
increases.
it increase. And what is the direction of the field?
Away from the magnet.
Away from magnet, toward the left hand, right hand side. Do you agree?
Mhm.
So in that case, according to Lenz law, what would be the direction of induced magnetic field?
Mhm.
Think about it.
The magnetic field.
Yes, induced. According to
Um,
Lenz law,
it would be towards the left.
toward the left hand side. That's right. Yes,
Mhm.
because originally there's nothing. Okay.
Yeah.
Okay. If so, what is the direction of induced current in the coil?
Mhm.
How can we work out that if the induced field is toward the left hand side inside the coil? What would be the direction of the current in the coil?
Would it be towards the right hand side?
No. You have used right hand.
How do I use the right hand rule?
You have always used right hand to work out the relation between the current direction and the direction of the induced magnetic field.
Would it move from positive to negative?
They have positive, right?
Yeah.
Yes, that's right. If you use the right
Mhm.
hand to hold this coil, and the thumb will give the direction of the magnetic field, and the forefinger will be direction of current. You are right.
Yeah.
Okay. So determine the direction of code. So can you write the answer here? The first answer is so that's exactly what is shown, right, in this diagram.
Mhm.
Okay.
Yeah.
Okay. Left on. So what do you mean left on? Just keep it on, or so
if it's left on, then eventually I think the current would stop being produced.
No. The second question is they just keep that current, right?
Mhm.
They keep that battery, keep the switch on the right hand side, right?
Mhm.
So in this case, do you think there is a current induced in the coil on the left hand side?
No, I don't
No.
think.
So we discussed before. That's right.
Mhm.
Okay. The third, what would happen if the switch is suddenly turned off?
Then there would be no current, I think.
Induced current? Why? My question is, does the magnetic field flux, does that magnetic flux change from the on to off?
Yes, it would.
Yes. It's a decrease, right?
Mhm.
It is decreased from some constant to zero everywhere.
Yeah.
Therefore, according to Faraday's law, they must have some induced voltage, and hence, because it's a closed circuit, therefore they must have some induced current. Now, in this case, according to Lenz law, what would be the direction of the induced current?
It would be towards the right.
Toward the right. Now it's hard to communicate. Can you draw something? I cannot draw. Can you draw something on your screen to indicate the last situation?
It would be if it's turned off.
Yes, turned off. The last case, the third case.
Then the current would move this way, I think.
Yes, that's right. Yes, that's right. Yeah.
Mhm.
In this case, current will move this way, which is opposite to the first scenario. Do you agree?
Yeah.
Okay, you have done it. Good. Let's move to, can you just search some other question in your textbook? Can you scroll down to see this Lenz law? Aha. There's another scenario. Yeah, can we try this one? Try yourself. Further practice with Lenz law. This time, this single. By the way, the single coil is called a loop, right? Because just for you the closed loop. So there you don't have to put ammeter, but you should be able to imagine that when in some under certain condition, according to Lenz law, the electron is moving in that loop, right? Okay, can you read this question first?
A coil is moved to the right and out of a magnetic field that is directed out of the page.
Yes.
Determining the direction of the induced current flow in the coil while the magnet is moving.
Right, good. Do you want to try? So when you see this circle with dot in the small circle with a dot at the center, which means the magnetic field is out of page, right? Is out of page. Okay. So that is the original direction of the magnetic field. And remember, this time, apart from this six circle, there's no magnetic field outside these 6 small circles. So what would happen if you move this coil? You have to consider 2 scenarios. One is that the circle covers the area, and another is area is partially outside that area, right? Okay, that direction is what's his direction is that is induced when the circle is inside the 6 circles or not?
Which this is when it's outside.
It's partially outside, right? Not completely, partially. So why do you choose that direction? Let me see. Yes, that's right. That is also out of page, right? Induced is also why?
Because with it moves out of the magnetic field
area,
it'll be going into the page. The magnetic field.
No, the flux will decrease. Yeah, you have to mention the flux because the area doesn't change, but the field strength decrease. So therefore, the flux change. So there must be current. Okay. Then you apply Lenz law. Good. Can you see it again? Can you explain again? According to
when
Lenz,
the flux changes, the magnetic field will be pointing into the page, and then I just
outside the page, out of page.
Oh yeah.
Originally it's out of page.
Yeah, and then you just do the direction that the current would move.
So what is the direction of the induced field, magnetic field?
Oh, it is counterclockwise. That
is the current, right? But the field, induced field is outside the page, right? That's right. Yeah, you're right.
Yeah.
So you understand the Lenz law, certainly. Yeah, you can go to next page to see if any other question we can discuss. Aha, can you see that the figure at left hand side, up left on the left? Yeah, that's right. Okay, that's a good question. So this time they squeeze, right? Or stretch, they stretch the coil. And the question, what can you read the figure to see what is the scenario?
A current is induced by changing the area of a coil.
Yes.
The amount of flux through the coil is reduced and an EMF is therefore induced during the time that the change is taking place.
Yeah.
The current flows in a direction that creates a field to oppose the reduction in flux into the page.
Yes. Do you understand this? Do you understand this, what they say? Can you imagine if you stretch this this coil, eventually the area becomes 0, right? So compared with original area, the A is in decrease, but the magnetic field is not is constant, right? But however, the magnetic field relatively speaking is getting weaker now. Do you agree?
Yeah.
Oh, sorry, the flux, magnetic flux is decreasing, although B is constant this time.
Yeah.
Magnetic field is a product of area and the magnetic field. In this case, magnetic field is constant, but the area is decreasing. Therefore, the flux is decreasing, right? According to Faraday, they must have some induced voltage, hence induced current. Okay. Now, according to Lenz law, what would be the direction? How can we fix that issue? How can the induced field will stop the changing in the magnetic field flux?
It will go to the right.
That is the induced, right? What is direction? Is the direction of induced field is towards into the page or out of page?
Into the page?
Yeah, into the page. Yeah, this time the field is into the page, right? Original field is here. You're right. You're right. How about next diagram? Do you understand next diagram, which is same scenario, right? Did they change something? Can you see the magnetic field is uniform? Is into the page, right? Into the page. This time they changed orientation. Okay, good scenario. So what would happen if you change the direction, the orientation of coil?
It will, the flux will decrease.
Flux will decrease, yes.
Because the area will decrease.
It also will decrease. So what is direction of induced field, induced current?
Into the page?
In this way, yeah, it's very hard. If you go to extreme, so basically the area, so basically this time the area is decreasing, right? The area increase, so therefore they have to ensure the induced field were in the same direction as the original magnetic field. Okay, but this time they didn't ask you the current direction because they only ask you to the EMF, right? Yeah. Because sometimes you have answers, you have to pay attention to the question. Sometimes they only need to know whether there is a EMF. Okay. Others they will ask you what is the direction of current. Okay. Yeah. Okay. I think that is all. Do you understand Lenz law now today? Yeah, I do. Okay, you can do more exercise. If you have trouble, we can discuss. Otherwise, you should be okay. All right. Yeah. Okay. Going to take a break now. See you next time.
Okay, see you. Thank you.
Okay, you're welcome. Goodbye.
Bye.
Stop that.